So this video goes over example 3, which is asking us to find the equation of a plane, and we have some information about that plane, but what we want to focus on is the fact that we are looking to find the equation of a plane, which means there are specific ingredients that we need in order to do that. To write the equation of a plane, you need a point on the plane, and you also need a normal vector to the plane. Now, the normal vector, what that really means is you're looking for a vector that is orthogonal to your plane. So our goal is to figure out how can we get some normal vector orthogonal to this plane. So we're looking for this in addition to a point on the plane, but the good news is they've already told us that the plane goes through the origin. We can see that here, the origin is shown here. And it also contains a line. So lines are given with their parametric equations, so this line in the plane here is pictured. So we've already been given a point on the plane. So our point on the plane is the origin. So 0, 0, 0. Now, there are infinitely many points on this plane, so you can pick any point that you want as long as you know that it's actually on the plane. The next thing we need to do is find our normal vector. And how we do that is going to depend on the given information that we have. Right now, we are told that we have a line that lives in our plane, and we're given the parametric equations of those lines, of that line. And lines come with, we know that equations of lines come with a slope vector associated with them, and that slope vector comes from the coefficients of the t's in the parametric equations. So you may prefer to rewrite these parametric equations stacked the way we did in our lecture. So we could think of this as x equals 2 plus the quantity 1 times t. Y equals -1, and we don't see a t there, so that means that the coefficient of t is 0 in the y equation. And then z equals, we don't see a number being added to it, so that means that that's a 0 plus -2t. And according to our equation, the parametric equations, the numbers that are being added are the coordinates of the point that we know is on the line. And the numbers that are the coefficients of the t's are the entries in the slope vector. So just to label that real quick, this is a point on the line, and then these other coefficients are telling me a vector v that is parallel to my line. So we have that pictured in our picture there. So starting out, right now I have a vector v, and I'm going to go ahead and write it out. That is 1, 0, -2, so I'm just using the coefficients of the t's. And right now that is parallel to the plane because it's parallel to the line, and the line lives in the plane. So if we could find a second vector that is also parallel to the plane, then we could cross them to get a vector that's normal to both of them, and hence normal to the plane. So our goal is to find another parallel vector, or another vector that is parallel to the plane, and then cross So we would find our normal vector n that we're looking for by crossing them, or crossing it with v. Well, looking at my picture, one way to get, if you ever want to find a vector that's parallel to a plane, if you have 2 points in the plane, you can just connect them, and then you have a displacement vector that necessarily has to be parallel to the plane. And I see that I have some vector, I have a point, the origin is in there, and then if I connect it to any point on the line, I would have a displacement vector that would then be parallel. So I could take the origin and find some point on the line and connect that. And if I do that, I'll have 2 vectors that are both parallel to the plane. And if you think about picking up this vector, I'll duplicate it and moving it. Then the cross product by definition is going to produce some third vector, n, that has to be perpendicular to both of them. And that's actually the n vector that we're looking for. Notice that the cross product that we just drew is parallel to something that we thought we were looking for. Alright, so I'm looking for this displacement vector, which comes from needing to know a point on the line, which is, we'll call Q. And I have a point on the line. I already know that I could use, from my equation of the line, I could use what my line is equal to, or my position on the line when t is 0. And when t is 0, I get 2, -1, 0, which is exactly those coordinates that I have highlighted in green there. And so I'm going to connect Q to the origin. But the good news is that that's a position vector. If I do Q minus the origin, I'm just going to get Q as a position vector. So that vector that we're going to get is going to be, so we're connecting O to Q, which is the same thing as just using the point Q as a position vector, which is just the entries of that vector, 2, -1, 0. So now I need to cross V and Q. So remember what we said we were going to do. We are going to let n, our normal vector, is going to be the cross product with our vector v that came from the line, and the vector q, which came from connecting the origin to a point on the line. So setting up the cross product, I know the top row should be I, J, K. The middle row should be that first vector in the cross, although in this case it won't matter because you'll just get plus or minus the value of the cross product even if you swap them, and that will still be something that's orthogonal. So I take V, which is 1, 0, -2, and Q, which is 2, -1, 0. I'm going to go ahead and do my determinant calculation. So I'm going to get I times, now what I'm doing here is when you remove I, you're basically thinking of crossing out the ith column, and this is the determinant here that I'm taking. And so I'm going to do 0 times 0 minus -1 times -2. So that will give me 0 minus -1 times -2 is just going to be 2. Then because the jth entry is always, the sign on it is always negative according to our cross product formula, then I come over here and I say, okay, cancel out the j column. My remaining matrix is going to be 1 times 0 minus 2 times negative 2. So I'm going to get times 0 minus, and we said 2 times negative 2, so that is plus 4. And then plus k, we cross out the kth column. When I cross out the kth column, my matrix that I'm left with, when I find its determinant, I'm doing 1 times negative 1 minus 2 times 0. So negative 1 minus 0. And so finalizing that, let's first write it out with the ijk notation. But you can also rewrite it as a vector if you feel more comfortable with the angle bracket notation. And then from there, we now have our normal vector. This is exactly what our first ingredient was, or sorry, our second ingredient. So we have our normal vector and we have our point on the plane. And so I just use my equation of a plane, which says you take the coefficients so the coefficients of x, y, and z are exactly the value, the entries in the normal vector, and then that's equal to dotting a normal vector with a point on the plane. We can use any point on the plane to do that dot product. So I'm going to do negative 2 times x minus 4 times y minus z. Because my entries are negative 2, negative 4, and negative 1, so that's where these coefficients are coming from. That will be equal to my normal vector dotted with my point that I know is on my plane. And remember, we know that a point on the plane was the origin. And anything dotted with the 0 vector is always just 0. So we don't even need to bother doing the computation because I would multiply corresponding components and add them up. But because there's the 0 in each of those products of corresponding components, that would cancel. And so this tells me that my final equation is negative 2x minus 4y minus z equals 0. And that is the equation of my plane.